no matter how hard you work and try, you will never be able to completely eliminate noise. But that doesn't mean that trying isn't fun. Hello, and welcome back. Today, I want to show you one of the power supplies I've been working on in the past few months, a circuit in which I tried to apply most of the noise reduction techniques we've been discussing in the past few episodes. It's not a perfect design, but at least for its intended purpose, it's adequate. Today's video is sponsored by JLC PCB. They provide easy, affordable, and reliable PCB and PCB assembly solutions, empowering electronics engineers to develop projects efficiently. For today's project, I went through multiple iterations of the design, multiple sample phases, and in all cases, JLC has provided top-notch products. Ordering a set of boards is as easy as dragging your Gerber files onto their website and setting a few configurations. Up to 8-layer boards can be obtained for as little as $2, and you can also get a $30 coupon for the 6-layer boards. So even larger PCB sizes can be obtained for only $5. Easy to use, affordable to make, and reliable. Check out the link in the description for more details. So let's start with a bit of context. The circuit I'm working on is an active loop antenna, basically a loop antenna with an amplifier attached to it, which is powered over the coax line through a bias T from 12 volts. Now, the challenging bit here is that the amplifier is built around a vacuum tube. Now, I will not be going into the main amplifier's design today, apart from mentioning that the vacuum tube needs two supply voltages. A 6.3 volt for the filament, for which I used a basic LM317 regulator. This is a linear regulator, so it does not present any noise concerns, but the other voltage that the circuit needs is a relatively high value. I set myself an 80 volt target. And here, we need a switching converter. And this circuit needs to be low noise enough to not affect the reception. So while I have no specific noise target value, like a certain amount of dBm, the main objective is to not overdrive the receiver and to still have a useful amplifier. Now, before you start thinking about why I didn't just go with a low voltage transistor amplifier, like a normal person would do, let's quickly turn our attention to the power supply. A boost converter with a charge pump voltage tripler stage on top of it. So if we look at the circuit, while it did suffer a bit of modifications over the various sample phases, it's fundamentally a boost converter with a charge pump stage added on top. So this set of diodes achieves a voltage tripling effect. Now, to adjust the final output voltage, I added in a trimming potentiometer, and while the supply is always enabled, so the enable or shutdown pin is always pulled high. Now, other than the purely functional components, I added in a few noise reduction methods. First, inside of the supply, in the switching node, I added in a snubber, and in series with two of the diodes, I also added in a set of ferrites. Now, outside of the main converter, I have a ferrite-based filter on the output and an inductor-based filter on the input. Now, my target was to achieve about 80 volts on the output, so most of my capacitors are either rated for 50 volts within the main boost converter and charge pump circuit, or 100 volts directly on the output. And while for the input, these are relatively low voltage capacitors, since you will only have about 12 volts here. Now, for safety reasons, I try to keep the output capacitor values as small as possible, so in case anything happens, there's very little charge in here. So now, let's start looking in a bit more detail how each of the various components were chosen and how the exact choices can impact the performance of the circuit. So first off, the main component, the converter. For this, I found two ICs with more or less the same functionality, the AP3012 from Diodes and the LMR64010 from Texas Instruments. These are both boost converters with integrated switches and fixed switching frequency. However, as a difference, the LMR is rated for higher voltages and higher currents compared to the AP3012, which is only rated for 29 volts, and it has a 500 milliamp switch. However, for the sake of the noise analysis, there is a very significant difference in between the two components. The exact way in which they switch. So while this parameter is not directly mentioned in the datasheet, what is highlighted though, if you scroll through it, is that the AP3012 has a bipolar transistor switch, whereas the LMR has a MOSFET switch. In general, MOSFETs switch faster than bipolar transistors. This is a good thing in almost every situation, except when noise is concerned. So if we check out the switching node for the same board, but with different control ICs, so on the left side we have the LMR64010, on the right side we have the AP3012, we can see a clear difference in the rise and fall times. Especially the fall time is smaller with the LMR. Now, a faster transition time means a more efficient supply, since this causes smaller losses, but this abrupt transition also means more noise. My oscilloscope is measuring 4 nanoseconds, but it might be even smaller. Anyway, this particular transition is also clearly visible in the output spectrum. While the low frequency ripple is more or less the same with both converters, so it's a different voltage scale, but the amplitudes are about the same, the smaller fall time of the AP3012 generates a lot less noise on the output, especially in this peak appearing at the tip of the ripple. So for this reason, I will be moving forwards with the AP3012 since it causes a bit less noise. Next component to analyze is the diode. So while the operation of this component is quite simple, there's a very wide range of practical components to choose from. And as with any good design, the first step is to properly understand what it is that you actually need. So the very first diode I started off with was the ES1F, a high voltage, 1 ampere rated, super fast diode. So while this component has a relatively low junction capacitance of about 10 picofarads, it also has a relatively large reverse recovery time of 35 nanoseconds. So while the circuit works just fine with this component, I also quickly realized that the 300 volts of reverse voltage rating is a bit higher than the actual requirements of an 80 volt supply, where each of the diodes in the voltage tripler only sees about a third of the actual output voltage. So the next diode that I tried was the SS14, a 40 volt rated Schottky type of diode. This should be better since Schottkys do not present reverse recovery, but this particular component does present a much higher 200 something picofarads of junction capacitance, which could cause issues. Now, a noteworthy advantage of this type of diode is the forward voltage drop. So this should be much lower than the PN type of diode. So using Schottky diodes, the supply should be more efficient. So if we first look at the switching node and compare the two implementations, so once using 5 ES1F diodes, once using 5 SS14 diodes, we can observe that the larger capacitance of the Schottky diode is causing the rise and fall times to be quite large. However, in a sense, this is helping to prevent the overshoot which is occurring with the PN diode. So the larger capacitance is not necessarily a bad thing. Now, if we turn to the output, we can see that the PN diodes are far more noisy. So the ripple is larger with this set of diodes compared to the Schottky ones. So taking both sets of measurements into account, we can conclude that the Schottky SS14 will perform better. But is this the best for this application though? The last thing that I ended up realizing upon closer inspection of the circuit simulation is that when I have about 80 volts of output at around 25 milliamps, so right now it's about 25.5, each diode, if we check, isn't just exposed to a maximum reverse voltage of just under 30 volts, but also if we check the currents through each of the diodes and we just ignore most of the spikes, the averages are around 25 milliamps, and even the peaks never really exceed 145 milliamps. So there is absolutely no need for a 1 ampere rated diode. Something much smaller can be used. Now, after a bit of searching for low current diodes, I chose two specific ones to test. The BAV99 a high-speed PN type of switching diode, which presents a very low junction capacitance of about 1.5 picofarads, as well as a 4 nanosecond reverse recovery time. And well, this diode comes in a very small package, so there's 2 diodes actually in one of these SOT23 packages. And the alternative to this that I tried is the BAT64 diode, which is a Schottky diode, and this also has the 2 diodes in one package possibility as well. So this is a fast recovery type of Schottky diode. Now, this diode does present a slightly larger junction capacitance of about 6 picofarads, and it also has a rated reverse recovery of 5 nanoseconds. These are both still very small values. However, since this is a Schottky, the forward voltage values are also much smaller. So this would be the preferred solution from an efficiency point of view. So first off, if we compare the switching nodes to the 2 implementations, so once using BAV99 diodes, once using BAT64, both diodes are performing quite similarly. There is not a big difference in the transition times, and they are both creating quite a bit of overshoot compared to the larger capacitance diodes that we started off with. However, since the BAT has a larger capacitance, it is making the over and undershoot a bit smaller. This extra capacitance is also making a very clear difference in the output, where the high frequency spikes have been drastically reduced, especially the one appearing in the tip of the ripple. So to continue, I will be sticking to the BAT64 diodes. To finish the analysis of the power stage, I will now focus on the inductor. So to start things off, I will stick to a powder core inductor to reduce the magnetic field emissions. But just what is the appropriate value that I should use? Should I go for a larger or a smaller inductor? So when your case size is fixed, the choice of inductor needs to take multiple parameters into account. First of all, you need to make sure that whatever inductor you're using will not be saturating or overheating. But then when it comes to noise, a larger inductor value will mean that a smaller current ripple will be going through your circuit, which is a good thing. But in general, a larger value also means a smaller self-resonant frequency, which is not so good. So if we check the input side noise with both a 10 microhenry as well as a 22 microhenry inductor, we can observe that the switching frequency ripple is indeed smaller for the larger value inductor. However, the peak-to-peak noise is larger since this is given by the high-frequency spikes, which are smaller for the small inductor, which has a higher self-resonant frequency. Now, in general, filtering noise is more difficult the higher the frequency of the noise is. So for this reason, I will stick to the smaller inductor. This might come back to haunt me a bit later though. Now that the main power stage components are fixed, it's time to see what can be done about all the remaining noise. While input and output filters are an option, let's first look at what can be reduced from within the supply. It's always best to reduce problems at the source rather than trying to band-aid things later. So if we look at the output voltage and the switching node at the same time, we can see that the larger high-frequency spike present on the output corresponds to the rising edge, which is also causing quite a bit of overshoot. So I will just try a generic RC snubber combination to fix it, and also monitor the exact peak value and rise time to make sure I'm not wasting too much energy. Now, I did foresee a placeholder for a snubber in the switching node, so next I will try to assemble this. Now, if we zoom in, unfortunately, there is no clear oscillation frequency to take advantage of to be able to fine-tune the snubber, so I will just take some random RC combinations and try to attenuate this. So first, I kept a fixed resistor value of 22 ohms and just played around with the capacitor. So I tried 100 picofarads, 220 picofarads, and 470 picofarads. And while the largest capacitor completely removed the overshoot, it also severely increased the rise time. Looking in more detail, you can observe that even the 220 picofarad capacitor creates a change in the slope. So to keep the circuit running as cleanly as possible, I will stick to a maximum of 100 picofarads. Fixing this, then I try to change the resistor. So starting from a high value of 22 ohms, I will increase the resistor by 1 ohm, and down to 4.7 ohms. Interestingly though, this did not really change things. So, in all three cases, the results were more or less the same. So I will be sticking to the 100 picofarads and 22 ohms combination. Finally, I just did a before and after comparison, just to confirm that we are on track. So these are both done for the same output load to make the comparison as accurate as possible. So while I do not have access to the transistor's driving circuit, providing a capacitive load in the switching node does seem to slow the transitions down a bit, and also contribute to reducing the output noise. Now, another measure to mention is that in the design, I did foresee some extra ferrites. So these are in series with two of the diodes. The idea with these was that they can damp the sudden charge transition in the multiplier cells. So when charge is traveling from the right side through the diodes to the inner capacitors, these elements should slow down the transition times. Now, while it's not really recommended to do this added inductance could end up destroying the diodes, I did try mounting these, and well, if we check the output, so comparing no ferrites to a design with the ferrites, we can see an interesting thing appearing in the output. So specifically the discontinuity that corresponds to the falling edge of the switching node, which is when the diodes with the ferrites are conducting, has completely disappeared on the second measurement. So I guess you could experiment with adding a few more ferrites on each of the other diodes to reduce the other spike, but at this point, only these two ferrites will have to do. So now that the converter is done, all the measures to reduce noise from within have been applied, it's time to look at the input and the output, and see what sort of external filtration methods can be used. So if we check the power supply's input, here we have a higher current, and the noise is mainly of low frequency. So it has an almost sine wave shape with very few high frequency spikes. So for this, I just added a basic LCE filter, so an extra 3.3 microhenry inductor and a 4.7 microfarad capacitor. So when choosing this inductor, I went for a semi-shielded coil, since usually these have higher self-resonance frequencies. So in this case, we are not expecting the inductor to radiate, but having low parallel capacitance is critical for keeping the noise in check. And with this filter added, the input no longer shows any sort of visible noise. So both the low frequency ripple as well as the high frequency spikes have completely disappeared. Now for the output, I wanted to do something a bit different. So here we are running lower currents, and we also have more high frequency noise. So here I decided to go for a ferrite based filter. So we start off with about 74.4 millivolts of noise, and after one ferrite, we are doing far better. So we still have some noticeable noise, especially some of the high frequency spikes are still left behind. So finally, I ended up doing a two-stage filter, where two ferrites are in series, and with this there's not much really left. I mean, it looks like there is, but since it's quite low frequency, I think that this is just noise picked up by the probe, rather than something inside of the trace. So we're done. There's no more noise, right? Well, not really. While most of the conducted noise, that is noise in the supply traces, was filtered out, we didn't really do anything about the radiated noise. In the final design, the supply is supposed to sit quite close to the amplifying element, so we're not out of the woods just yet. First thing to consider is the proximity between the noise source, our power supply, and the sensitive circuit, the amplifying vacuum tube. To keep things rather compact, I did not really leave too much space, so that's that. However, there is one final cost-neutral measure that we can apply, making the power supply face away from the vacuum tube. So in the very first design, I did not take this into account, but in the last sample, the board was made to face towards the wall. In a later iteration, for thermal reasons, vacuum tubes are quite hot after all, I also added in this copper PCB as a shielding wall. So this should also help with mitigating any remaining noise. Now, from a layout point of view, I went for a 4-layer board, which might seem a bit over-designed. However, this was done for two reasons. First of all, I wanted to have right beneath my circuit a solid ground plane. And this had to be as close to the power supply as possible. So that's why this is the very first layer beneath the circuit. Now, the other thing that I wanted to do was a bit of ground separation. So the circuit on the first layer, as well as the one beneath it, are the noisy power supply ground. And now the other layers, so the third and the fourth, as well as the edges on the first two layers, are the shield ground, which is not so noisy. And while the two grounds are interconnected on the fourth layer. Now, whether this actually helps or not, I cannot honestly confirm, but this sort of measure is sometimes used in certain designs. Anyway, let's now see the complete circuit in action. So, if we turn on the complete SDR setup, first with the amplifier off, so the bias voltage is off, this shows our noise floor. So I'm measuring from 0 up to 20 MHz. So whatever we do with our filters, we will never get any of these spikes to go away. However, things get a bit more interesting when we actually turn on the amplifier. So in this case, we do get some extra spikes appearing, which are not there in the previous measurement. So these are quite periodic. It's actually the fundamental at about 1.5 MHz, and then the various upper harmonics. So double the frequency, triple, 4 times, 5 times, and so on. So it's very clear that the supply is not perfect, and the noise is visible in what the amplifier is picking up. Now, in the first experiment, I left the supply completely unshielded, and this is obviously not sufficient. So the first thing to try is a low-cost shielding approach, using a conductive tape of aluminum. This will work if you contact it to ground, but also make sure that it does not contact the circuit. So extra care needs to be taken so it doesn't short out something. With this, so if we compare the no shield with the aluminum tape shield, things get a bit better. So almost all of the spikes have been reduced by some amount, and especially the spike around 7 MHz has completely disappeared. Now, when it comes to shielding, there are proper solder-on shields available. So this is the next thing that I tried. So what I used is a 2-piece shield. So with this, the lid can be taken off to inspect the circuit. And well, when we assemble this and compare the aluminum tape shield with the 2-piece shield, we are doing a bit better. So again, all of the spikes have been reduced, and even the one around 6 MHz and the one below 5 MHz have completely disappeared. Now, just as a bonus, this particular design did go through 3 different layouts, through which I improved things step by step. The last one being the one that I used for most of the measurements today. However, if we check out these with the actual amplifier, well, the very first implementation was really bad. I mean, this sort of noise spectrum would make the amplifier completely unusable. Now, with my second attempt, things have been improved, so all of these spikes have been reduced by at least 10 to 20 decibels, but things were still not great. Finally, with the third implementation, the one that we've been testing today, things are far better, but there's still a bit to improve on this. However, I'll be leaving things like this for now. Now, after a sleepless night, there was one more thing I wanted to try though. Since the main noise source is the fundamental switching frequency, let's try to specifically address that. So the first thing that I did was to try to add some output capacitance. So I added an extra 1 microfarad capacitor to the output. And this did indeed reduce the output noise, the ripple amplitude has decreased. However, this did not change the noise spectrum picked up by the SDR. However, what did improve on things was a change in the inductor. So rather than the 10 microhenry inductor I started off with, I tried a 22 microhenry inductor. So this reduced almost all of the spikes by at least 5 decibels. So to end things, I will be leaving this 22 microhenry inductor in the design. In the end, while not a perfect solution, this power supply does seem to be low noise enough to be usable. So most of the noise spikes are not all that bad and are mainly located outside of the lower ham bands. You might find a bit more noise at higher frequencies, but this particular amplifier wasn't really designed to work there anyway. Now, designing low noise switching converters is hard, but I hope that this series helped you a bit with some of the techniques and steps needed to create a good design. So with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.